Thank you so much. It's been wonderful to be here already this morning. And one of my challenges is figuring out when I was here last. And I think I pointed it to at least a century, and that's the past century. And I also figured out a decade, but I still don't know the date. I was hoping to find it in my, in some of my seminar notes. But it's great to be back. And when I was here last, I was a full-time theorist, so I would have given a very different talk at the time. And now I became more of a leader of experiments, which is super exciting, but there's always theory to be done, and so it's a great hybrid. And so I'll be telling you about, at this point, one of it is real, so you could see a launch of a balloon payload, and that was SPB1. So I'll be talking about two different efforts. One that is under EUSO. So let me tell you what that acronym stands for now. It stands for Extreme Universe Space Observatory. I'll introduce that again. And SPB stands for Super Pressure Balloon. So this is SPB over here, and that is EUSO over there. And we've launched one balloon, and we are now building a second balloon payload. The first one we launched is a refractor, which looks like a very tall refrigerator. And now we're building reflectors, so two telescopes, one looking down for ultra-high-energy cosmic rays and one looking towards the limb of the Earth that eventually will be for neutrinos, but for now it's really to test the ability to see neutrinos. And at the same time, I'm leading a sort of conceptual design, which we have done in preparation for what's called Astro 2020. You might have heard your neighbor down south has this huge effort this year to plan for the next decade in the US for funding. And we were one of the 10 probe class missions chosen by NASA to be studied as a conceptual design. And we led this effort, which ended recently. And we're now basically writing all the implications of that conceptual design, and that is POEMMA. And POEMMA, I like the acronym a lot better. If you have to come up with acronyms, please think of something easy to remember but doesn't spell correctly, because if it spells exactly like poema in Portuguese, which would be without one M, then you never find it on the web, right? So two M's makes it harder to find. But then you can remember what it is, and so it's a poem in Portuguese or Spanish. And the actual acronym is PROBE, which is this class of below $1 billion scale missions of, so we're using of here, extreme multi-messenger astrophysics. And the multi-messenger comes from the fact that we can observe two types of messengers, not gravitational waves, but we can look at ultra-high-energy cosmic rays, and this is shown here as a shower that we see from above, hard to do in 2 dimensions here properly. And then we have neutrinos, which are coming from the other side of the Earth, producing a tau lepton, which decays and makes an upward-going shower. So by looking at upward-going showers and down-going showers, we can see both neutrinos this way and ultra-high-energy cosmic rays that way. And those are protons and all the way to iron, as far as we know. So the questions we would like to answer are can be put into these 3 categories. One is, what are the sources of the ultra-high energy cosmic rays? These are pretty striking as far as their energies are concerned. I think theorists would not have predicted them to be there because they're too energetic for most back of the envelopes. But it's not impossible to explain them astrophysically, but it wouldn't have occurred to us that these things are going on if we hadn't observed them. And the other is, what are the sources of cosmic neutrinos? And we know now from IceCube many neutrinos at sort of the below PeV level. And the types we are talking about here are above tens of PeVs. So, energetic, very energetic, not as energetic as those, but energetic enough. And I'll show you some theories that actually are easier to detect in this energy range. And then, the real dream is not just to understand what are the sources, but how do these sources accelerate to these energies? What type of particle physics can we learn by having such high energy accelerators in the universe, so using the universe as a laboratory? Can we understand something new about, for example, extra dimensions, supermassive dark matter, topological defects, all the fun things that one might speculate, but very hard to test in laboratory-bound accelerators? And just on the cosmic ray history, so cosmic rays we know exist since 1912, and that again involved a balloon, but a simpler version of a balloon, and people inside. We don't send our people up 33 kilometers without oxygen, bad idea. So, but Victor Hess did, a few kilometers up. And they were pretty courageous folks, and they showed that cosmic rays, or these ionizing radiation, is coming from outside the Earth. The majority of the flux is not produced on Earth, and that's that famous balloon flight. In contrast to cosmic rays, we have photons as the favorite astronomy tools, and they have 14 orders of magnitude in energy, if we call all of these things energy. From gamma rays to radio waves, and I'm pretty sure you already saw this in many outreach classes. And I want to bring this just to contrast the numbers of orders of magnitude that we have in cosmic rays is similar. Okay, so as you know, when you look from radio to gamma rays, you don't see the same exact phenomena out there. So it's not ridiculous to expect that cosmic rays are not going to be the same phenomena across 14 orders of magnitude, 12 orders of magnitude that we know well. And then gamma rays also continue for quite a bunch of orders of magnitude, and the techniques for very high energy gamma rays and cosmic rays are similar. These again are showers in the atmosphere. And then neutrinos are starting to become interesting. I mean, there are low energy neutrinos from supernovae and from the sun, but at the sort of pointing back to the source level, trying to get outside of the atmospheric background, that starts just below PeVs, at TeVs, at tens of TeVs. And that's ice cube. Okay, but in principle, they should be going. And then if you just want to do astronomy and astrophysics in all orders of magnitude, you can extend it another bunch of orders of magnitude all the way to pulsar timing by using gravitational waves. And I think the fact that LIGO has seen what it's seen makes everybody very excited about being able to look at systems with at least 2, maybe 3, maybe 4 messengers, right? So different types of measurements so the multi-wavelength, now it's multi-messenger in that sense. All right, so the rest of the talks about cosmic rays and neutrinos, we'll come back to some gravitational waves, but to simplify for those who are not used to cosmic rays, this is one way to show the simpler version of those orders of magnitude. So 12 orders of magnitude in energy, unfortunately 30 orders of magnitude in flux, meaning these things are pretty steep, which means it's very hard to detect, but also that there are different things happening to them. So at very low energies, the solar system is important. So the magnetic field of the sun keeps the particles rotating around. So these are all ionized protons and other elements, but these are basically nuclei. So ionized hydrogen up to iron, say. And then in the low energies, the sun makes a difference, so you have to understand the solar system. But as you move up in energy, it's galactic cosmic rays. So these are known to be coming from the galaxy, mostly from indirect measurements, because they are not pointing back to the galactic plane, because they have charge and there's magnetic fields, so they come around and they show up mostly isotropically. But we know that at the very highest energies, they're not isotropic and they do not show the galactic plane. So the dipole measurement of Auger, which I'll show you in a few slides, pretty much tells us this is above 8 times 10 to the 18 electron volts. So above, around here, these are extragalactic. We don't know when extragalactics take over from galactic, so this transition is ill understood. And if it's simple, if it comes back and forth, as I'll show you, it's a little more messy. But what I'll be focusing on the cosmic rays are the very highest energy ones, where things should simplify enough, both in the sense that you run out of most accelerators. It's too energetic for most things to reach those energies. But also, the magnetic fields start letting high rigidity particles come through, so you should be able to point back at about here. So as the flux is going down, the easier to do astronomy. Okay, so astronomy starts here, which is really hard to do. Now,
so is there literature on why that looks so continuous, whereas it might have been discontinuous?
Yeah, why isn't there more structure? Hold that until I show you tons of structure. Okay, so this is the way one can, yeah, you'll see soon. Anyway, so the low energy detections, we can do very precise measurements of cosmic rays by going above our atmosphere and putting detectors in situ, and the biggest action, and this is in space, the biggest action in terms of low energy cosmic ray measurements has been due to the alpha magnetic spectrometer that's sitting for years in the ISS, in the International Space Station, and they are planning on an upgrade, and so they should be living there a little bit longer, and those have been giving us very good measurements of lots of different species. For the very heavy nuclei, then one can do still the best with balloons. And then ground experiments, which are these indirect measurements. So for the very low fluxes, we need to use alternative techniques to be able to catch one of these things, and I'll tell you more about it. But let's make the simple thing a little less simple. So here is the same thing. So the flux of cosmic rays multiplied by e to the 2.7. Let me use, I love these pointers, there. So that, the main dive is taken out. And so now you can see that it's not straight. It's full of bumps and wiggles, right? I'm going to focus over here. But just to give you a sense, since many of you don't hear about cosmic rays very often, there is the knee, which we have known for quite some time, and that is assumed to be basic, and we know a little bit more, which I'll show you in the next slide. It's assumed to be when the galactic acceleration is starting to lose energy. So, you have some power law injection, you have mostly protons at the lower energies, and then you become iron rich, and then you dive. And then in principle, who knows? This second bump is was not predicted, let's put it that way, and it's very interesting right now. Lots of people in the community trying to understand what that second bump is. Then, if you're going down in flux, that probably means that you're running out of whatever your accelerator is. If you're coming with sort of a steeper flux, that means going this way, going harder. That means probably some new source, some new, or maybe a new element. Well, it could be one or the other, right? I'll show you what the composition is in a second. And so this probably is a new element or a new accelerator, and maybe it is where the extragalactic stuff takes over. But maybe the extragalactic stuff takes over here, and this is some sort of other transition. And so there's a lot of physics to be discussed here. And so since we're not pointing back and we don't know exactly who's sending us which cosmic ray, the other thing we can do is look at the composition. So the composition is shown here in a compilation, and there's tons of systematics, because as you remember, we're doing very different measurements. So the other thing I wish to make clear here is that it changes colors all the time. It's not the same detector measuring all through these orders of magnitude. So every time, within, say, the black dots, which is Auger, we kind of do very good ways of scaling the energy, and we believe that the relative energy is very well known. But if you have some systematics compared to, say, another measurement in the same range, and the Auger prediction is 14%, and this is a power law in energy, so these dots move in some diagonal here. And so if you want, you can say these guys have to move down, or you have to move up, because these should be consistent measurements.
So the two curves, instead of probing different parts of the sky.
Yeah, this is in the northern hemisphere, this is in the southern hemisphere, but
the difference is not statistical.
I think these differences are systematic effects. However, if you look over here, which is what I was telling you earlier, these might be real, right? So once you scale those two together, then everybody's on top of each other except for some of these points. But then it's just before you have very low statistics. So it could be a fluctuation, it could be a source. But before that, because here the rigidity starts to give up, and so you could have more in one hemisphere than the other. But below that, everything is, mixed up diffusely by the magnetic field, so these should be the same flux everywhere. So the fact that there is some thickness here is basically these systematics between one experiment and the other. Okay, so having this shape of the knee in each experiment is very good measurements, but the fact that they're not on top of each other has to do with the systematics between them. And eventually we get to low enough energies, and that's around here, where we can actually do experiments in the lab.
Quick question. So
Sure.
I'm just looking at the scaling. Sorry if you mentioned this and I missed it. Is there a good physical motivation for scaling
To 2.7? No, just because it's easier to put on a plot. Sometimes, yeah, if you live over here, we multiply by e to the cube, for example. But depending on where you sit, you multiply by a different number. But it does, this is the best to get this part flat. So although this one, J, it doesn't say, yeah, this is 2.6, you know. So they do 2.6 to get this flat, and then everything else is a structure. So if you had a constant power law, it would keep on going like this, but it actually comes down and all that fun stuff. And here is, you know, the turbulent water is underneath. So it looks pretty simple in my first slide. It's much messier when you start looking at each element. So red is protons. So protons dominate, and helium are just behind protons. And then, you know, if you put them together, they have sort of a reasonable behavior, although there's lots of discussion why is helium taking over from protons ahead of time. But, you know, this is, you know, in the community, don't want to go there yet. It's too detailed a discussion right now. But, you know, proton peaks here. And then the iron peaks there. That's one way to explain the second peak. So this first one is the proton coming down, and then the second one is the iron coming down. This is, yeah, in terms of Z. Yeah, so this is Z times that. Well, roughly. Actually, no. No, it is okay. I mean, you have to put in what power laws are taking over from which and how are they decaying. Because the problem that is here, you see the protons are returning. So it's not super easy to know if you plot this to E cube or to E, it's going to peak in different parts, right? So you need to also model this next component coming up to know that this is where you expect. But yeah, what they call Peter cycles, or, you know, Z-dependent. Sorry, this is losses. Z-dependent losses are fine. Rigidity-dependent losses for the explanation of these two. This one is very hard to explain, this next peak of the protons. But you could say maybe that is where the extragalactic took over, or maybe there's something else going on in the galaxy that makes those things show up. And then you have another peak of protons and a follow-up by iron at the highest energy. So this part is the one that we are working the most on. And this ankle here is quite interesting too, but this other, the fall, I'll show you the science, the physics behind it. But let me talk about how do we measure these things a little bit more before we get into modeling it. So space, you can do that directly. Here, the flux is about 1 per meter square per year. So in principle, you can make, you know, on the ground, a very big detector. Here, you get to 0.1 per kilometer square per century. So this is my challenge, okay? Now, the good news, so the bad news is, you know, you're going to sit for a century, and you might find a tenth of particle in a kilometer square detector. But the atmosphere is really the detector for us, not a direct detection. If we put it in space, even if you had all that money, you wouldn't catch anything. But the fact that each of these particles gets to shower in the atmosphere is the trick to making it something we can see. So extensive air showers are something that in 1937, Pierre Roget said should be the explanation for the fact that when he put detectors on the ground, from time to time, all of them were hit at the same time, roughly. And that is a pancake of particles coming down because they have the same origin. And this was back in the late 30s. Here is a 10 to the 14 electron volt proton simulation. So here we're just following the core of that particle. So if the particle continued, we would be with it. But these are the particles sort of growing, the shower growing around it. The electromagnetic part of the cascade is in red. You have hadrons in blue, neutrons in green, and muons in gray. You can put detectors on the ground. For this kind of energy, the right sort of separation is hundreds of meters. So in 1.5 kilometers, you get from the sort of peak of the shower all the way to a tail. And the electromagnetic part of the cascade is the brightest, so that's what you usually see with detectors. But you can also see muons and neutrons and hadrons, and as you get closer and closer to the core, you can get overwhelmed. But by placing detectors at different distances, you can sample this shower. Then there's the other technique, which is here is as a function of altitude, you're getting the shower developing, peaking, and then dying off. And you can see that directly in the atmosphere, and that is due to fluorescence of our atmosphere. So if you have a shower developing, like in this image here, in the atmosphere, at night, every time it will develop in the atmosphere, but at night you can pick up the signal from nitrogen fluorescence. So these particles, electromagnetic part of the cascade, will shake the nitrogen around, it will fluoresce in UV, and if you have a very sensitive UV telescope, that can follow very fast moving things, so it can't be CCDs. We use PMTs for that. You can see a light bulb moving at the speed of light very fast. So the two ways that we can look at showers, so three ways. One is on the ground, like I showed you before. Another way is through this fluorescence emission, which is isotropic, and it's very nice because you can sit, tens or hundreds of kilometers away, and you can see the shower developing if you have the right equipment. And then there's a third way, which is the Cherenkov, which is coming right down the sort of line of sight if you start from the trajectory of the particle. And that's, for example, what the gamma ray people do with CTA, Veritas, CTA not yet, in the future, Veritas, Magic, and who am I missing? HESS. Right? So what they're looking at is this one that's very collimated. It's within sort of a degree or so of the shower itself, and you just sit below it, which is fine if there's lots of these things hitting you. But if you have 1 per kilometer square per century, that's not very practical. Okay, so you need to, we don't use Cherenkov for the cosmic rays, but that's exactly what we're going to use for the neutrinos, because they are going to be coming, we know where they're coming from, which is the limb of the Earth, and then we should see this emission directly coming at us. Okay? So for the cosmic ray data at the highest energies, the two experiments that one pays attention to is a telescope array in Utah. That's a 5 collaboration effort with covering 700 kilometers squares in the Utah area, close to the city of Delta, with 3 fluorescence telescopes. And then we have the Pierre Observatory that I worked since 95. Again, previous century, previous millennium. And we covered 3,000 kilometers squares in the Argentinian Pampas, in the Pampas Amarillas, which are just south of the city of Mendoza, in the region of Mendoza. And we have 4 fluorescence telescopes. So this is the leader of the field. Here's a telescope array on the map with their detectors. They have different types of detectors. They use scintillators. On the ground, we use water tanks, as you'll see shortly. But we both use the same type of technology for this at night observing, which are using telescopes to look at the fluorescence emission. And here you see one actual shower developing in this camera and the double decker that they have. Jim Cronin at the University of Chicago got me interested in this by asking me about magnetic fields. I was looking into the evolution of cosmic magnetic fields from primordial times to today. And he asked, when can we, at what energy can cosmic rays point back? And the answer was, if it's protons, it's likely to be 10 to the 20, but we don't know for sure because we have limits on how strong magnetic fields can be in the intergalactic medium, but we don't actually know what the number is. So, and the limits depend on how fast they are fluctuating. So I said, you're actually going to be measuring these fields yourself. So that was when I got involved. And here's just an outreach video that we did with the shower developing. In yellow would be the detection on the ground. The distance between each of these yellow dots is about a mile, so it's 1.5 kilometers. And then we have the Superman effect, which I didn't catch. So folks who designed this decided that the light comes from the telescope to the shower. But it should be the other way around, as you all know. But here you go, right? So these should be traced that way. But pay attention to outreach things, or you get a lot of people ill-informed. Here's an image of these detectors. This is 1.5 kilometers from that one, and another one over there. There are 1,600 of them. And now they're being upgraded to separate the muons from the electromagnetic cascade so we can do better measurements of the composition to higher energies. And these are the 4 telescopes that are doing fluorescence. So the original idea for both the EUSO effort and the POEMMA effort is to bring one of these things and put them up instead of down. When you're sitting on some place, you can look at the sky above you, right? But you can't see much more air than this, about 4 pi or so. When you go up in the sky, you can see a lot more of the atmosphere at the same time with one eye. So it's a much more efficient way to get to very high statistics at the highest energies. So this is what, if we look at just the Auger data here at the end, this is a really nice measurement. You see how precise the error bars are, meaning they're below these dots, until we get to the very highest energies. Here is the science we can test in the laboratory. So this is PP collisions at LHC at 10 to the 4 GeV in the central collisions. And you see this second knee structure very clearly. You see the ankle very clearly, and then the turnaround. And what I want to do is get a lot more data here, because as soon as we get closer to this highest energies is when things are starting to be really exciting. So the first thing that got exciting is the extragalactic component coming in, and that we know is at least above 8 EeV. EeV is not defined. EeV is 10 to the 18. It must have been defined in an earlier slide. And so we know from here onwards, the data shows a dipole that I'll show in the next slide. It's possible that it starts much earlier, coming from extragalactic sources, but then the dipole is too weak to show up with the data we have. Way too much data, and also the lower the energy, the more the magnetic field turns things around. So here's the dipole above 8 EeV at a 6.5%. And this is what it looks like in equatorial coordinates and galactic coordinates and in supergalactic coordinates. If you look at galactic coordinates, if it was coming from the galaxy, which should be here, and this is the center of the galaxy, unlike some other plots, you don't see anything towards the center. That is the actual opposite direction. And this is where the dipole is pointing. This is the position it should point if it's pointing to just the mass without any consideration of magnetic fields. And if, so this is the 2MRS, so the redshift survey of 2 mass. And this is what the dipole from within 100 megaparsecs would give you. And these, for things which are further than 100 megaparsecs, these protons and iron, they get either the photons associated or they get pion production. So we have a horizon for these particles, which makes it easier to get a dipole. If it was infinite, then we wouldn't get a dipole. And that. Why do you sit back there? Lovely. Thank you, Dick. How are you?
The CMB dipole is sort of in between. Is that point?
Well, I didn't know. We didn't put it here. But it is somewhere not too far. Not identical.
If one's going up further, that is the convergence point.
Right. But we are not sampling that far. Yeah. But the magnetic field effect of the galaxy alone would push these things this direction. Okay, and these are what these 2 arrows are for 2 EeV and 5 EeV, given the rigidity and given the knowledge, which is not 100%, of our galactic magnetic field. So it's becoming extragalactic. The other fun thing that's happening just when the dive is happening is that sources are starting to show up in the sense of correlations. So we have an old claim that it correlated with AGN. So this is the latest on that story. It did get weaker, the correlation with AGN. And if you do a gamma selected, so Fermi selected AGN sample, you get a correlation at the 3.1 sigma. And if you do starburst galaxies as your sample, then you get a 4.5 sigma. So they seem to be, the cosmic ray anisotropies seem to correlate, or the bursts or the little hot spots seem to correlate better with starburst galaxies. It's still below a 5 sigma, and so the next round of Auger should be able to tell us.
It's larger than 32.
Yes, this is at the, this is what I, so it's over here. Yes. The audience doesn't know what that means yet, according to my plan, but we will talk about this. So anyway, this is, either starburst or AGN, and some folks happen to be both. This is sort of really trying to get a simple 0th order direction for where the accelerators might be living. This is not saying we know it's starburst, but it seems to correlate a little bit more, and it's not 5 sigma yet. And what I mentioned before is that this is also when we're running out of data, which is why this is where my focus for these projects is to how to make the very highest energy ones. We know they're there, but the flux is really low. How to get an order of magnitude or 2 improvement over there. And he just mentioned the GZK. So this dive could be because the accelerators in the universe stopped accelerating particles, right? So it's already a stretch to get to 10 to the 20, and then you just run out of either containment or energy or whatever it is that makes these things reach that. So maximum energy is a very simple explanation for a dive. Another one is that it's actually an effect of propagation in the intergalactic space, in extragalactic space. So the first such proposal was done just as soon as the microwave background without its anisotropies was discovered, and that is due to Greisen, Zatsepin, and Kuzmin, Greisen in the US and Zatsepin and Kuzmin in the Soviet Union at the time, that both groups said, there will be a limit, a cosmological limit to how far you could see cosmic rays. And that is due to the fact that, take protons, for example, there will be an energy loss due to interactions with the microwave background. So for a proton of 10 to the 20 electron volts, the microwave background is a gamma ray background, not a microwave background. And that means that all kinds of things will happen to this proton, including first step will be a delta resonance production of pions, and then multi-pion production at higher energy. So these will make the proton that you have left be lower energy than the one you began with, and this neutron will become a proton again. So basically it means that you're going to end up with a pileup of lower energy protons and a dive in the flux around 10 to the 20. So this is shown here. This is continuous losses due to E plus E minus production, and then you have the wall due to these kinds of pion productions for protons. For nuclei, similar things happen, and those groups also mention that, because not only you can produce pions, but you can also photodissociate, so you basically break the iron into small components, neutrons and protons, so again you end up with lower energy protons and neutrons. So basically it's very hard to imagine you have very high energy past 10 to the 20, so that's a natural barrier. However, this is 100 megaparsecs, this is 10 megaparsecs, and we don't know exactly what happens here due to radio emission and other fun things, but basically you get, in the infrared, but you get, maybe local sources, right? So you could see at 10 to the 21, something which is 10 megaparsecs away, but you won't see a gigaparsec away.
How energetic would the original particle have to be to make a neutron that doesn't have time to decay on its background?
So the neutron, let me answer it the way I remember, meaning because I calculated it. A neutron at 10 to the 18 can make it from the center of our galaxy to us. Okay, so above that energy, it could come from further away. But that's rough, which is why we looked for neutron. For 10 to the 18, we looked for, if they are galactic sources, then neutrons will give us this anisotropy towards a galactic center, and we didn't find any. So that's another suggestion that these are extragalactic. But that was one way of probing a galactic option for 10 to the 18, because they would have made it. All right. Now this is an interesting barrier for the protons, but that also means we have a whole new source of neutrinos that come from exactly the same interactions. We also have a source of gamma rays. So pi naughts will give you gamma rays, but those will not make it here usually because they will interact with this background and again lose energy. But the neutrinos can come all the way. The only challenge is to get them. And I'm sure you know neutrinos. I'm going to skip that. Sometimes I talk to folks that forget where they are in the table of elements, down in the bottom. It's also important to remember how fun neutrinos can be for physics. So these are the solar neutrino and atmospheric, solar neutrino and, supernova 87.8 neutrino Nobel Prize. And more recently, solar neutrino and atmospheric neutrino doing oscillations. So let me just take the Nobel Prizes out and show you what I'm talking about. So there is, in principle, just like the CMB, a cosmological neutrino background, very hard to detect. So any young postdoc or graduate student who wants to take that question up, that's an interesting one. Solar was pretty impressive that one could do that. Ray Davis started that early. Supernova, we didn't know when it was going to happen, and people are building lots of detectors for the next one. Hopefully the detectors will be ready just on time because Betelgeuse is playing up, right? Then you have what is not astrophysical, it's atmospheric, meaning cosmic rays producing neutrinos, and they can be producing, coming down, or they can be producing neutrinos on the other side of the Earth. And that's how you can do some physics with the oscillations of neutrinos, which can get you a Nobel Prize. Then comes the astrophysical finally. This was a long coming challenge, and IceCube finally was able to get rid of the green and start looking at the pink. And the one I just mentioned is this brown. So we are talking about 10 to the 18 as the energy typical for the neutrinos from the GZK effect. While the astrophysical depends on the model, but it probably starts, probably starts at lower energies, but you can only get over the atmospheric a little bit later, and IceCube has been able to do that, so we're very excited. Here's a plot of IceCube neutrinos, and just to give you a sense of, when does the atmospheric neutrino get out of the way, it's about 10 to the 6 GeV or so. So we're going to be talking about from here onwards, and POEMMA will be doing the job further that way. All right, so the way to answer these questions, this last one is the fun one that all the theorists can have fun with. In terms of measurements, these are two things one can practically do. For the cosmic rays is to measure the spectrum, the composition, and the isotropies or anisotropies above 10 eV, 10 eV, so 10 to the 19 electron volts. That's when things start getting interesting, and we run out of data, so we need more statistics there. And then for the multi-messenger coincidence with gamma rays and gravitational waves, neutrinos are really exciting if we can get them. So IceCube has been already looking for coincidences with gravitational waves, and Auger too. And the type that we can do with the projects we are working on is around 10 PeV and above. So as I'll show you, it's sort of complementary to IceCube type things. Okay, so let me tell you about the conceptual design. So this is POEMMA, the probe of extreme multi-messenger astrophysics.
For a second, and go back to the concept of what the source is going to be. Has there been sufficient theoretical understanding to basically tie to the ultra-high energy cosmic rays to, let's say, a star formation rate in a galaxy?
No. Yeah, just we are still, remember, what was it? The first X-ray measurements, with a rocket, you go up and you say, it's hotter this way than that way. And there seems to be, an X1 that way. Yeah, so I think there is a, let me answer that question in a different way. I think the theoretical, let's go here. The theoretical, there is improvement in theory and some really interesting models, both because we can simulate things better, but the part that made theory a lot easier to do is this one, right? So when you do protons all the way to the highest energies, then you really run out of accelerators, right? So you basically have, nobody can reach that energy. But once you put, a Z of 26, something simpler can do it. For example, I always worked with, pulsars as my favorite, because you have, or magnetars, you have very high magnetic fields and small amount. And this is sort of the Hillis plot, which I have one in the back slides. We can spend more time, but I hear you guys have another talk to go to, so we'll go fast. But anyway, so when, you had red all the way to there, you ran out of places you could contain these particles, let alone accelerate them. But now that you have 26 less energy to put into these particles, right? Because the Z here is a lot, helps you an order of magnitude, then there's a lot more stuff going on. Now, what are the best models for starburst galaxies? No idea. There's a lot of AGN models. Starburst galaxies is sort of a later discovery from the correlation people. And so I think that is a good place for people to work. But there are people working on shocks that make intergalactic, very large cluster shocks. And a lot of the models, in my opinion, will be sort of ruled out or proven by their neutrino counterparts, right? So if you have, say, a magnetar inside a newborn, these are usually very young pulsars, inside a supernova, you get a lot different types of neutrino sources than if it's an AGN shock or if it's something from the intergalactic medium. So you will have more neutrinos or fewer neutrinos and different spectrum neutrinos. So I think the neutrinos are going to be the ones that tell us, but it's really nice if we can have a combination of ultra high energy cosmic rays pointing to the right directions in the sky and a model for what the neutrinos that came from them look like. So those two, I think, are going to make us a little better in the theory world.
I have a question.
Mm-hmm.
Also, I'm not sure why is the iron flux is comparable to proton flux if the iron in the cosmic balance is much lower?
In terms of the how much iron we have around, right? Yeah. So if you look at where we begin, then it's fine. It's just stuff in the interstellar medium. At the low energy cosmic rays, the ratios are not ridiculous. Oh, and by the way, this is energy, not energy per baryon, so that's important when you're making comparisons. But anyway, so the fluxes here are reasonably explained by taking the interstellar medium and throwing into an accelerator. And that accelerator is supernova remnants, for example, right, at the low energy. So that seems to make sense. When you come to higher energies, it got really a mess, right? So you have things that are escaping the galaxy and therefore going down in flux because they're not contained and they're not adding to your environment. And new things coming up with different power laws. And the trick of making it all work together is not obvious. So there's a lot of theory, but I think it's not easy to tell them apart. And none of them are like, of course. But the lower energy ones, I think, is pretty under control. But at the highest energies, it's a little harder. All right. So I'm going to go into my other world, which is designing fun things. And I didn't do that alone for sure. This is the group that put together within a year a whole conceptual design with the help of engineers from Goddard Space Flight Center. And we have in white all the American institutions and people in them and the international folks that work with us. So it's about 16 institutions from folks who worked on an earlier version called OWL, EUSO, Auger, TA, Veritas, CTA, Fermi, and Theris. So this is a real effort from a whole community that cares about the highest energies. And the POEMMA design is 2 eyes because we want to have very good measurements of the shower development in the atmosphere. And separating protons from iron, it really needs sort of a stereo vision. With monovision, you can so you always see a line with monovision, but you don't know if the line is next to your nose or far away, right? As the atmosphere is exponential, if you only have mono, you could still estimate where this thing is, and you get the direction, no problem. But you can estimate roughly where it is, because it should be peaking at some region, so you give a probability. But if you have 2 eyes, you don't have to do any of this stuff, right? So you get a really good measurement. So having 2 eyes is what we started with, but obviously, NASA asks you a question. If you lose one of them, can you still do science? Of course we can. We still get the direction. All right. So 2 eyes for stereo vision, and the stereo vision is key for the composition measurement, and it also helps with the energy. But the energy is basically colorimetric, so you just pile up all that light, and you have a number. If you're looking down with the kind of optics we developed, which is 45 degrees, you see pretty much all of Lake Michigan, 3 times Lake Michigan, let's put it that way. And then the other way of looking for upward going showers from neutrinos, and I think I should have turned this around. I don't know. Yeah, it seems like that's the beginning. Anyway, so this should be the beginning, and that's the end. We basically are looking at the limb of the Earth from 525 kilometers up. So in terms of scale, the limb of the Earth in our field of view is roughly staying in the East Coast, looking at most of the West Coast, okay? And so you can do, with this type of search for neutrinos, you can also do ultra-energy cosmic rays in all this volume too, right? But the further away, the harder it is to see these things. Here's the teams of engineers that worked with us, scientists, and they were very patient with us. Here's the look of what we developed. So this is as simple as it gets, is a Schmidt optics with wide field of view request, the 45 field of view. It's a mirror, a camera, a lens, which makes, sort of optimizes the light that deviates the light from the camera so you get more light. And the thing NASA hates is these doors that open and close, because our camera is quite sensitive to light. So either we have to be very sure that we're not pointing to anything very bright, or we just shut it down every time we go in the sunny side of the orbit. The orbit is 95 minutes, and we designed it to be operating 100% for 3 years with a 5-year goal. And we also wanted to fit into one launcher, because the launches had the price tag, so you could pack everything you wanted in one launch, but if you had to have 2 launches, it's twice the price, so we did that kind of thing, and it works, actually. But the 4 meter is, the size of the mirror is this diameter. Now, these mirrors are more like light buckets or photometers, meaning they just collect light and they roughly send it up to the camera and are, within 0.3 degrees, we're good, right? So it's not something like the optical astronomers would build, which means it's much cheaper than something like a 4-meter optical telescope. The fun part is this camera, which I'm very proud of coming up with a crazy idea, which is to try to do 2 different sciences with the same mirror. So in blue is very fast, microsecond scale cameras, which we have built many to see the light from the ultra energy cosmic rays. So we're looking at ultraviolet lines, just like the telescope array little video, that go through these blue boxes. Each of these boxes is something we have, so each of these black squares that have all these different units in them is what we call a photodetector module. And the total, it's 55 of these photodetector modules that we have built a few of those. And we have flown and done many tests in the balloon program with those. And the total is about 126,000 pixels for these cameras. And these are photomultiplier tubes. They're super fun. And then we have another camera on top. So this would be the idea of putting the Earth limb right here or somewhere, or just scanning with the red as a source is setting on the limb of the Earth. So if you're looking, if you know there's a gravitational wave in this direction, and we happen to be flying like this, you just point towards where the source is, hopefully when you're in the dark, and you follow that source until it shouldn't be emitting neutrinos anymore at these energies. So either the source is setting or is rising on this part of the camera. But the difference here, well, first is silicon PMs instead of glass, but also the timing. So we want to take pictures every 10 nanoseconds, because that's the time scale for the Cherenkov cone coming through us, okay? So for example, we can point these things in many different directions, but for example, let's take a cross-eyed vision, and you can look in, with a stereo for ultra-energy cosmic rays in the middle, which would be the red points are places where you could see a shower with both cameras. And then in green, you can only see mono, so you could do cosmic rays there. And then right at the limb, you're looking at these sources of neutrinos with the other part of the camera, okay? And we have all the details of the actual mission. If you have questions, I'll tell you about it. But basically, we're sitting at 525 kilometers, an inclination of 28 degrees. This is just a choice that makes it cheaper to launch. It's roughly where Hubble is flying around. But the important thing is that we're not going like this, like the Earth is, right? So if you are sitting with a detector, say, in the pole, in the ice cube, and you're looking for things that are skimming through the Earth, you're only going to see them coming from very small amounts of the sky, because you're basically looking in these directions and you're rotating like that, not like that. So if you rotate like this, you can see the whole sky, okay? All right, that's important. So for the ultra-energy cosmic rays, this is our, from nadir to limb, you begin coming up, and then you sort of sit after 5 years, an order of magnitude above what the ground would be, extrapolated to be doing in the 30s. And so we reach the much higher statistics for all the different sources. So our prediction is that we could definitely see if it is either one or the other, either the Starburst galaxies or the AGN. We would be very, very, very bright hotspots. Here is a comparison of the telescope array in black and Auger in green, and this is where we would be for 10 to the 21, 10 to the 20th, and around there. So basically the order of magnitude, but also we have the full sky coverage, which is with the same instrument, which is a problem right now with both telescopes. And then we have this fun part, which we spend more time because we hadn't actually, many people have speculated about it, but not done all the calculations involved. And it turns out that it's actually quite powerful. So for example, it is clear that the strongest signal, the easiest to find, is from tau neutrinos. Okay? But astrophysical things will produce muon and electron neutrinos, but they oscillate on their way here, so we would have 1 and 1 and 1, so 3% will be in tau, so that's what we'll be seeing the most. We are right now doing a calculation that shows that probably the muon neutrinos would be seeable too, but a much easier, much harder to, like maybe 10% of the time we would see a muon generated shower. But the tau is real easy by comparison. You get a new tau of, say 10 PeV, 100 PeV. It goes through the Earth. It interacts at some point on the Earth and makes a tau. And the tau needs to be generated just before it leaves and decays, and then it starts a shower just above the ground. Okay, so you look down and you try to see something coming at you from that point. We spent some time making a list of all possible theories for different neutrino productions at these energies. I'll show you a couple examples, but you won't be surprised if neutron star mergers are an obvious place to get some neutrinos from. So this is something that we used the Fang and Metzger calculation. We have some wild speculation about black hole coalescence. Obviously, you need some hadronic stuff around. It can't be just pure black holes, but they have pretty large estimates. We have tidal disruption effects. Blazar flares would produce, but they are pretty far away, so it's not super easy to necessarily get them below, say, 40 megaparsecs. So this is which distances we would see these sources for at least one event. This is what are the number of events at 3 megaparsec and at the galactic center, right? So for tidal disruption, that applies. So you could have 10 to the 8 neutrinos. For 3 megaparsecs, 10 to the 3, and so forth. So these are some of the sort of background stories that we're trying to figure out what are the best targets for us. And here would be what we would be doing, right? So you have the POEMMA satellites going around, observing towards the limb of the Earth, and pointing in this direction if the source is in that direction, but the source could be in this direction or in that direction, and we would turn it around to the right place. But remember, we are using the Earth, right? So, for example, if you think of the sun in Sweden in the summer, it never sets, right? So there's some sources that will never set, and some sources that will be setting for a long period, like the sun in the winter in Sweden, right? So or in Canada, but depending on where you are. Therefore, so here's a plot. Forget the others for now. This is a plot of turning off the sun and asking which, so imagine there's no sun, but you do have sources rotating around you. Are we already? Oops, I have to finish. Yeah, people have to go. Please go.
Well, only a subset.
All right, those who have to go, don't feel bad. Bye. All right, so this is the sun that never sets in white. And in red is the sun that sets for a long period. And the sun that sets for a long period is an order of magnitude more, we are 1 order of magnitude more sensitive to those sources than if they are sort of in the middle. So in dark purple is the middle emission that we would observe for a different model. And the light one is what we would see for sources that happen to be in those, setting for a long period times. And then obviously for the whites, we don't see anything. And then the sun takes a bite out of this, is a little bit less than half. As the Earth processes, we see the rest of the sky. So, whatever was setting, just like Sweden, we will start seeing it at some point. So we see the whole sky eventually, but it takes, maybe a month or so to see some pieces of the sky. It could be longer. So we split the sensitivity for fast bursts. So fast bursts, we would have to be lucky or unlucky, right? So if the source is in the white, we don't see it at all. If it's in the red, we see a lot of it. But most of the time, we'll have this in the blue, which would be this piece. And here is Auger limit on the neutron star gravitational wave, and ice cube. And we can go, if it's in the right position, all the way to 1 order of magnitude below, but we're always more sensitive, but even more. And here's one model of Kimura et al. That goes right through the sort of fast burst one. But the very short bursts are harder to see. The very long ones are actually quite easy in comparison. So again, the same geometry type thing, but variation is a little smaller because obviously this is one position. If you have a month later, like thousands of seconds or 10 to the 5 seconds, like in the Fang and Metzger case, then you can go and reach the lower, sort of the more sensitive part of POEMMA just by the fact that we're moving around. So again, we can see these models quite well. Obviously, it depends on the distance to the source. And this is just what I said, but in a plot, that IceCube can see very well a piece of the sky, and it's sort of stuck in that region. This is a galactic plane. And the yellow is the most neutrinos they will see. For us, we see more actually in the complementary part of the sky, but we also see the part that they see. So it's very nice in terms of complementarity. All right, so I added one more way of doing neutrinos just because we were talking about this probably at lunch. And this is at very high energy neutrinos. So if you go for 10 to the 20, 10 to the 21, 22, and so forth, you can also see neutrinos. And here's the sensitivity for POEMMA. This is the neutrino flux from crazy models like moduli fields and things like that, so topological defects and other leftovers. And these are the radio detections in ANITA of the same thing. So we were just talking about this. And all right, so that's to give you a sense of POEMMA. And let me go to what we're doing right now. So POEMMA will be able to do, just to summarize, two things: 20 PeV neutrinos, above 20 PeV neutrinos, and above 20 eV ultra-energy cosmic rays, and do orders of magnitude better than what we have in the ground. And that would help us understand things quite well at the highest energies. So I mentioned the balloon program. But POEMMA is based on, OW, EUSO, and these balloon programs and an idea called CHANT. But let me tell you just a little bit about the balloons, because these are the things we're actually working on all the time right now. The balloons are part of this EUSO idea. The EUSO idea was to put a detector in the space station, and it's gotten many versions of it. Most recently, the Russians are leading the idea of putting something there. We have actually something called mini EUSO inside the space station that just started operating in the fall. And in the meantime, we've done 2 balloon flights. We also have a telescope in the ground, all with these detectors that look at microsecond time scale images of fluorescence. And POEMMA is the sort of goal. This is the first overnight flight called EUSO Balloon, was done in Canada, and was launched from Timmins, and it landed on a lake. And because it was just an overnight flight, we were pretty sure we wouldn't see an ultra-energy cosmic rays. So we put a lucky graduate student into a helicopter with a laser and produced a fake ultra-energy cosmic ray, and that's coming up right now. So that's what an ultra-energy cosmic ray looks like, and this is the integrated video of that image. Then we put together a balloon payload that could last for 100 days. That was the goal. And that's the super pressure balloon strategy from NASA. And this is, again, a refractor, 2 lenses, and that same type of camera, the one that I showed you before, which POEMMA is built upon. And here's us in Wanaka, New Zealand, just before it finally launched. And we have, graduate students, undergraduates, all kinds of folks. This is the launch date. That was really fun. I'll show you a video at the end. And this is the sad story. So at launch already, it seemed like we were going up, staying at this. So the idea of superpressure balloons is for 100 days, it should sit at 110,000 feet. However, we had a leak. So already bumping around, and then eventually third day, it was looking pretty bad. And it kept coming down. So we kept dropping ballast and coming back up again. But it wasn't exactly the conditions we had prepared to be observing in. So we got enough data to show that everything worked. If we were sitting there, we would see more. But we couldn't really do a ton with the data we got. And NASA decided to drop us next to the Easter Island. And this was 12 days. Now, 12 days, if we have the right winds, we should have gone, and we weren't going up and down. So if we are staying at 33 kilometers like we are planned to be, then in 4 days you're going over Argentina and Chile and coming around and around. So the idea is that in 100 days you're going to go over land, either here or there in Australia, over there a few times, and then you choose to come down. This is how they did it. The first test flight of superpressure balloons was 32 days. And when they got over to Australia, they brought it down. So there was no leak in this case. This one actually lasted 46 days, cozy. It changes color when it sort of closes a loop, although it closed here. But anyway, that is going around again. But again, here they started having leaks, and that meant that they had up and down flight. When you change altitude, you also change patterns of winds, and you end up in chaotic motions around the ocean, which is not super fun. And then our very sad story. So we're building a new payload that should be going in 2022. Sorry?
You said it came down and maybe survived.
No. The idea when you are dropped in the ocean is to go deep down and drag the balloon with you. We actually had floaters when we fell in the lake in Canada. We were floating and we recovered it. But in the ocean, they want us to bring the balloon down with us so that no ships and other things get interfered by a very, very large balloon. It's the size of a football field, so you don't want that thing floating on the water. Here's what we built for the inside the space station, and it's now in the Russian module in a UV transparent window doing all the background measurements that we need. And this is what we're building now. This is the design of it. It's the fluorescence looking down and Cherenkov looking at the limb, but we're not quite looking for neutrinos yet. What we want to show is the technique works, so we're going to look for ultra-high-energy cosmic rays above the limb that will be producing the exact Cherenkov emission that we would then use to look for neutrinos. So by studying the cosmic rays in this direction instead of going down, so this is above the limb, we should show that if there were neutrinos with those energies coming from the ground, we could reconstruct them. And here is one of the mirrors. These are the elements of the camera. That's what the camera design and the mirror design looks like. Here's a bunch of folks from Chicago who are working on this. I thank everybody for all their effort. And I'm ready to finish by reminding you that I discussed 2 projects we are working on that use the atmosphere as a particle observatory, right? And these are particles of the highest energies, both the highest energy neutrinos. If we were to see 20 PeV and above, that would be certainly the record keepers on those. And we have the ultra-energy cosmic rays, which we know for a long period, but we still don't know the sources. And hopefully new astrophysics and physics will come out of these observations. Thank you very much. I'll be giving you, just for fun, the launch, because it's always fun to watch a launch, I think, with little people moving around. Anyway, thank you. Questions?
So let's take maybe 1 or 2, and then we can.
What's the obstacle that to the Earth to 10 to the 20 of electron volt neutrino?
So a 10 to the 20 is very hard to see. So the 10 to the 20 that we are observing are actually showering horizontally on the atmosphere. So it's more like the ultra-high-energy cosmic rays than the ones from the ground.
But when you the question I ask is when you say you're using neutrinos to distinguish between possible sources.
Yeah, but these would be lower energy ones, right? So for a source that's producing the cosmic rays at 10 to the 20, the neutrinos will be at least at 10 to the 18 or below. And so, yeah. We're not accelerating the neutrinos. We're accelerating the hadrons that then produce neutrinos, right? So for example, the pion production gives you 10 to the 18. 10 to 100, depending on, the process. Yeah. And then, yeah, right. Pretty much.
Final question? If not,
has NASA figured out why the balloons?
They are working on it. One answer might be that little, this guy. That's the culprit right now. It wasn't supposed to unplug immediately. It was supposed to unplug much further up, and it happened earlier, so there's something funny about it.
Like what balloons small to begin with, bigger higher up?
Yeah, it's certainly, so they want to concentrate, because if it becomes fluffy, then it's a mess, right? So the color is they haven't figured that one out yet.
So how do they get rid of them?
Right, so it's a little thing that unplugs them, but it's not supposed to happen now. It's supposed to happen further after it's up. So if you, yeah, let me jump to where it was. So 2 tricks, right? So you want this thing to be past you. This guy is the lucky guy who makes that decision, right? So that you don't release it and it falls on you.
It is falling already.
Yeah, so it unplugged before it was supposed to.
So I think it was the same phenomenon. Glass TNG, which just
They use those
in
same
Antarctica.
Yeah.
You also had the collar, and the collar hit the experiment, and that screwed things up. So
Yeah.
there's a real.
The guy gets really hot.
You would have expected would have been sort of a fail, but.
Yeah. They don't have, you know, it's not the most supported part of NASA, ballooning. It's sort of a bunch of very courageous folks and a small budget. So, but you know, the actual balloon seems to survive, but if you don't mess up with it, right? So this is the problem. So the launch is usually where things go funny. And so the color seems to be the culprit right now.
Okay, let's take Angela one more time.